So today we're going to introduce conditional probability. Earlier we talked about the probability of an event. So this looks overly complicated, but this would just be like, what's the probability that you flip a coin and you get heads? So there's only one heads on the coin, so the size of the event would be 1. That would be the favorable outcome. And then the sample space is 2 because you have a heads and a tails. So the probability of flipping a coin and getting a heads would just be 1/2. If you had the probability of rolling an even number on a 6-sided die. So there are 3 different ways that could occur out of 6 possible totals. So 3 6 would be 1/2. Today we are going to talk about conditional probability. And conditional probability is a principle that relates the probability that a certain event will occur based on the fact that a previous event has already occurred. So conditional probability refers to the chance that some outcome A occurs given B has already occurred. All right, so basically what this says right here is this is the intersection of A and B. So at the intersection, that means both A and B have already occurred. And when you have a conditional probability, it restricts your sample space. And so now we're only talking about basically the probability of event B. So let's look at one. A card is drawn from a deck of cards. Determine the probability that it is a jack given it is a face card. So when you see the word given, that it is a face card, that is going to restrict it. So we want the probability that you draw a jack given you've already drawn a face card. So you have to know a little bit about cards. So there are 4 jacks in a deck of cards. And there are 12 face cards in a deck of cards. So the probability of A intersect B is the probability that both A and B occur. So this is a probability that I get a jack and a face card. So that's redundant because a jack is a face card, divided by the probability that you draw a face card. So there are 4 jacks in the deck, and there are 12 face cards in the deck. And so when you reduce that, you get 1/3. Number 2 says, what's the probability of drawing a heart given you already drew a red card? So this given right here is your denominator. So we want the probability that I draw a heart given I've already drawn a red card. All right, so how many hearts are in the deck? 13, because each suit has 13 cards in it. And half the cards are red and half the cards are black. And there are 52 total, so 52 divided by 2 means that I have 26 red cards. So I want the probability that I have a heart and it is red divided by the probability that I've already drawn a red card. So there are 13 hearts divided by 26 red cards. So there is a 1 in 2 probability that my card will in fact be a heart. Number 3, what's the probability of drawing a king given I've already drawn a face card? So this is just like number 1, except now we're talking about kings. So I want the probability that I draw a king given I've drawn a face card. The kings, there are 4 of them, and the face cards, there are 12 of them. So there is a 4 in 12 chance that I'm going to get a king if I've already drawn a face card, and that reduces down to 1/3. What's the probability of rolling a 6 given you've already rolled an even number? All right, so I want the probability that I draw a 6 given an even number. So I want the probability of 6 and even divided by the probability that it is even. All right, so a 6 and even, there's only one of those on a die, and the probability that you get an even one, there are 3 of those on the die. It could be the 2, the 4, or the 6. That is a fully reduced fraction, and that one is good. I have a bag with some marbles in it. What's the probability of pulling a red marble given I've already pulled a blue marble? I want the probability that I draw red given I drew a blue one. So this is the probability that I get a blue and a red marble divided by the probability that I've drawn a blue marble. So there aren't 2 shaded marbles. They're either red or blue or green. So there are no marbles that are both blue and red. There are 3 blue marbles. And so the probability of this occurring is 0. You cannot pull a red one after you've drawn a blue one. All right, next page. All right, so now we have some two-way tables. So this says I surveyed 100 students to determine their preference for after-school activities. So there is my grand total of 100. I have the freshmen, the sophomores, the juniors, the seniors, and I polled them about their sports, their clubs, their volunteering. What do they like to do after school? So all of this is determined by how the condition or how the question reads. What's the probability that a randomly selected student is a junior? So the randomly selected student, that phrase right there is indicating that I'm talking about everyone, and so therefore my denominator is 100. And when I look at my juniors, I have a total of 20 juniors that I polled. So that would be, what is the probability? 20 out of 100. Sometimes it'll want the answer as a fraction. Sometimes it'll want it as a fully reduced fraction. Sometimes it'll want a decimal. And sometimes it'll want a percent. So we've converted fractions to decimals to percents many times, so you should be able to accomplish that. What's the probability that a randomly selected student prefers club activities, prefers clubs? Randomly selected student means that my denominator is 100. I'm talking about everybody. And this time, we're going to have to follow the row over, and the row total here is 40. So 40 students prefer clubs. And you could reduce that many different ways. What's the probability that a randomly selected student is a freshman? Randomly selected, we seem to be talking about everybody. freshmen. Now we're back to looking at a column, and its total is 27. Right now we're going to have to do some conditional probabilities. If the selected student is a senior, what's the probability they prefer sports? All right, so conditional probability is going to restrict it to either a row or a column. In the conditional, you're going to look for the words if or given. All right, so this says, if the person is a senior, what is the probability that they prefer sports? So I am writing the probability of the sports to the seniors. So whatever is after the word if or given, that tells you what your denominator is. So if you're looking up here for the seniors, I am now restricting everything to that column. I only care about the seniors. So there were 8 that prefer sports out of 19 seniors. And so that's how I got 8 out of 19. Next one says, if they prefer volunteering, what's the probability they are a sophomore? So if they prefer volunteering, that is your denominator, and your sophomores are your numerator. All right, so on this one, the volunteering is a row. So there were 15 people that prefer volunteering, so therefore that is my denominator. And when you look back up, there are 5 sophomores that prefer volunteering. What's the probability that a student is a junior given they prefer clubs? All right, so I see the word given. It comes in the second half of the sentence. That's okay. Sometimes it will. So my denominator is that they prefer clubs, and the numerator is junior. So I'm going to write a ratio of juniors to clubs, given they prefer clubs. All right, so now I'm looking at the green, and they are a junior, so looks like it's going to be 7 out of 40. Last one starts with the word given. Given you're in a sport, what's the probability you're a senior? All right, so now the sport is my denominator, and the senior is the numerator. So the sport is 45. All right, so now I'm only allowed to use the sports row, and there are 8 seniors out of the 45 that prefer sports. The next one says, what's the probability that a randomly selected student is a freshman and prefers sports? All right, so when you see the word and, the word and means you're looking for the intersection of those. The probability that a randomly selected student, So I seem to be talking about everybody. I don't see the word if or given, so I'm talking about everybody. But now I want freshmen who prefer sports. So freshmen and sports, they intersect at 12. So 12 freshmen prefer sports. There we go. What's the probability that a student is a sophomore and prefers clubs? All right, so when you see the word and, you're looking for the intersection. My denominator is 100. When I look up at the top, the intersection of sophomore and club is 14. Complementary. All right, so something either happens or it does not happen. So complementary means that it does not. So if you take the probability that something does happen plus the probability that something does not happen, you always get 100. No, that's a percent. We're going to go 1 today. Yeah. So if it happens and does not happen, then that always adds up to 1 or 100%. What's the probability that a randomly selected student does not prefer sports? All right. So the randomly selected student, that phrase indicates that we're talking about everybody, and they do not like sports. All right, so 45 people like sports. Therefore, the people in the clubs don't like sports, and the volunteering people don't like sports. And so therefore, it is these 40 plus these 15. So we have 55 out of 100 that do not prefer sports. Are students more likely to prefer sports or volunteering? All right, so when I looked at my total, there were 45 out of 100 that prefer sports. And for volunteering, there were 15 out of 100. And so students are more likely to prefer sports because that is a bigger percentage. 45% is bigger than 15%. Which grade has the highest probability of choosing clubs? So when I looked at the clubs, the freshmen were 10 out of 40. The sophomores, 14 out of 40. The juniors were 7 out of 40. And the seniors were 9 out of 40. And so the choosing clubs is your denominator. And the 14 is the biggest. Therefore, if you did top divided by bottom, that would be the largest percentage. Sometimes instead of setting something up with a two-way table, we could set it up with a Venn diagram. So a Venn diagram puts people into categories. So this is a survey with 128 families. That 128 is your total. That is playing the S right here. So the S is the total, and you have 128. C are people with a credit card. L are people with a car loan, or I'm just going to use loan. And then we have this intersection. So I have people with a credit card. The pink is going to be people with a loan. So in a Venn diagram, we have this intersection right here. So at the intersection, they have both a credit card and a car loan. These 45 only have a credit card, these 12 only have a car loan, and these 10 have neither. So how many people have a credit card? So 45 and the 61 in the intersection, there are 106 families with a credit card. How many people have a car loan? So that's my pink circle. So I have 61 in the intersection plus 12. 73 people have a car loan. How many people have both? So that is the intersection. And there are 61 right there. Find the probability that a randomly selected family has a credit card. So I want the credit cards divided by the total. So we just said that 106 families have a credit card. And up there it said that my grand total is 128. So 106 out of 128 have a credit card. Find the probability that a randomly selected family has both a credit card and a car loan. All right, so 61 have both, and it's inferring that we're talking about everybody. So 61 out of 128. Find the probability that a randomly selected family has neither. There were 10 out of 128 that have neither. Last one. At summer camp, we have 60 kids that are sailing, 25 that take pottery. Right, so the two things that we seem to be talking about are sailing and pottery. There are a total of 60 that like sailing and a total of 25 that like pottery. 100 take neither. And 12 are taking both. So you have to go find out how much your overlap is before you start filling in the rest of the Venn diagram. So that is the first thing always. How many people are in both? How many are in that overlap area? So the sailing consists of the ones that only sailed and the 12 in the overlap. So you're actually going to have to subtract. 60 minus 12 is 48 that did sailing only. And then over here in the pottery one, so we need to take the overlap into account. So 25 did pottery minus the 12 that are in the overlap. 13 only did pottery. What's the probability a child is taking a pottery class? So the first thing that you really need to do is add everything up and get your totals. So I kind of ignored those and I went 48 plus 12 plus 13 plus 100, and I have 173 people at camp. What's the probability that they're taking a pottery class? So 25 are those and those out of 173. What's the probability that they're not taking any classes? So 100 are taking neither out of 173. All right, and that is it for today.